Our first speaker is Gabriele Bunkheila, and he is a senior product manager at MathWorks, where he coordinates the strategy of MATLAB toolboxes for audio and DSP. And that's actually really exciting because I just realized that everywhere I worked in my career in the music tech industry, people would use MATLAB as like the standard tool for DSP. But I've never actually met anyone before who worked on this software. So really nice to meet you here tonight, and really looking forward to your talk, creating audio plugins with MATLAB.
Yes, and I'm going to be streaming this video from my desktop. So if there's anything that wrong with the sound, please let me know so I can fix it right away.
And if you have questions, then feel free to ask them in the YouTube chat, and then Gabriele can answer them live here after the talk.
Great. And here's Gabriele.
Hello, thank you for tuning in. It's a pleasure to be here, albeit virtually. So my thanks also go to Josh and the audio programmer for the invitation. My name is Gabriele Bunkheila. I work with MathWorks, the makers of MATLAB and Simulink, where I work in product management for our products for signal audio processing. A few words about this content. The title is Creating Audio Plugins with MATLAB. This is not yet another talk to introduce you to a new software tools to create commercially viable audio plugins. This is more specific. This is a workflow designed for people who are familiar with digital audio processing and hence very often also with MATLAB to take their algorithmic, their math, their ideas and translate them into an audio plugin, which is a tool to verify and validate, test that the algorithms they put together is sound from an aesthetic or functional perspective. Okay, it's important for me to let you know that this whole workflow has been, so to speak, honored or celebrated for the third time this year in a competition that we MathWorks have been organizing with AES, the Audio Engineering Society. It's called MATLAB Plugin AES Student Competition. This is the web page. I'll show you where to get these slides later on, so you'll be immediately able to access these hyperlinks. So the competition is open to students. If you're a student, I highly encourage to go there and have a read. I'll mention more of this competition later on. Right, before we get started, I thought about making a version that's a bit more live than the traditional agenda. I'll show you a video. It's going to be a bit dense, but it's going to go in just over 2 minutes over the main topics that I'll cover during this session. I'll hit play, I'll let you watch. Don't expect you need to understand everything, but try to follow, and then we'll go more slowly into these steps. Okay, I'll make no assumption that you've been able to grasp every detail of this video, but hopefully something stuck and you'll be able to follow more easily what follows. So let me start by discussing the agenda in a more traditional way. So we'll start with a short introduction to MATLAB with a simple audio processing task such as the one that you've just seen. We'll discuss how to take that MATLAB code that is generic and refactor in a way that is ready to create and generate an audio plugin, always using MATLAB code. We'll discuss how to turn that MATLAB code into an actual VST plugin, and a few words in terms of the basics of how to be able to take that VST plugin and use it within a DAW, a digital audio workstation. So this won't be covering a lot of things. We won't have a ton of time. 40 minutes just fly, and we've already used a few. So let me get started and jump directly to MATLAB. Okay, I'll start by showing you something quite specific, which is a MATLAB live script. This is not something that has existed for the whole MATLAB history, but something similar to, say a notebook in Python. It's a mix of code, you can see here and here with a great background, and a numbered line of text to comment and describe what's in the code, and to separate the code into sections that can be executed independently. And then there will be some of the visual output created by the code. Okay, so this is an easier way to remember what you've done and to share it with others. Let me show you what I have here. At line 1 and 2, I'm defining a file name, which is a file that I have here in my working folder where I'm now. And based on that file name, I'm opening the content and I'm importing the data in that file. So it's an audio file, it's an MP3 file. So as an output, I'll get the audio samples and the sample rate. Let's execute this and see that as I do that, I've created a few variables here in my MATLAB workspace. Let's take a look at what these are. The simplest one is the sample rate, okay, 44.1 kilohertz, and that was the metadata in my audio file. And then I have the actual audio samples. Okay, there's a long number here. The important aspect here is to understand that this is an n, a long number, by 2. It's an array. It's a matrix composed of 2 columns. Each column holds the samples of a channel. Okay, first column is left, second column is the right channel. Okay, I can take that data and plot it as I'm doing here. Before plotting it, I'm doing something else. I'm creating a time vector associated to my data. So I can do that based on the sample rate. I create a sampling period here by doing 1 over fs, and I'm multiplying that sampling period by a number of subsequent integers going from 0 to the length of my samples. So the length is the largest dimension of the matrix here. So this large number n, let's call it, and subtracting 1 because I'm going to 0 to n minus 1. Okay, so sample period by the integers from 0 to n minus 1 gives me the exact time instance associated with my sample. So I can then plot t data, so the time against my samples, and get this plot down here. Okay, this plot down here will display all the values of my sample. You'll see the name was funky drum, so you see all these percussive events. We'll see more in detail in a minute. It goes from time 0 to about just under 25 seconds, so quite long to listen. So I'm sparing you that just for now. You can zoom in and see that, yeah, I do have, say, here, I do have two channels here, left and right. I can see the right channel on top of the left channel. As I do modifications on my plot, I've got some code that I can use to update it, my existing code, if I want, just by clicking a button. But let me move on here and show you what I have in the following. Okay, so now in the following, I'm narrowing my attention to only the first 3 seconds of those signals, because that will make it easier to iterate, do something with that data, and listen to it more quickly. So how do I do that? I'm showing you the 3 typical ways of indexing, as we call it, or referring to a content of the whole data that we have. For the time, I'm defining a new time of only 3 seconds by saying that I'm interested in only that portion of this time vector where its own values are less than 3 seconds. This is called logical indexing. This operation inside here creates a vector of logical values, true or false, 0 or 1, and only where this condition is satisfied, I will have 1. And the output t only gets those values at this time where the condition inside the brackets equals true or 1. Okay, so this will be a shorter time vector than the one that we had created earlier. And then here I'm using a more classical way to index into my original array of samples. I'm selecting separately the rows that I want and the columns that I want. And in the middle, there's a comma. So to the left of the comma, there's the rows that I want. Here are all the rows from 1 to the length of this vector that I've just created. Okay, these are, again, the sequence of integers that I create using this column operator. This is a pretty popular MATLAB operator. Okay, remember that MATLAB has 1 based indexing, so 1 will be the first row in this case of this array data. And then here for the columns, I'm using this column operator in a slightly different fashion. Okay, just column means all the columns in this matrix. So all the dimension numbers in here. I could have written 1 column 2, and this would have been all the integers between 1 and 2, so 1 and 2. Just putting down column and shows me that I'm considering all the dimensions in this dimensions here. Okay, and then I'm just doing the same thing as before. So I'm plotting x, and this is some prettification of the plot. Let me execute this. And after that, we'll see that we have something like what we had before, with some axis legends, time in seconds, and sample values, customized legend, left and right channel, something easier to understand when you share it with somebody. Okay, so this gives me some insight. I could optionally, if I wanted to, also easily listen to the samples by using a command like sound, for example, x and the sample rate in this case. By saying sound sc, sound scaled, I'm also taking my audio vector and normalizing so its minimum and maximum are between 1 and 1. So I ensure that I don't clip or I don't have a dynamic range that's too low. Let's listen to that together. It's 3 seconds. Okay, so this is a stereo signal. We played both left and right channels. If we went back to our workspace, we would realize that all the things that we've done were reflected here. For example, X is now an array with the same number of columns, 2 as my original data, but a lot fewer samples. In this case, just over 130,000 samples, okay, by 2. And my vector T has the same number of values as my new array. Okay, now it's where here in this script I do something with that audio data. So what do I do with it? Again, the column operator here. I'm creating a new array left made of all the rows, remember the column operator, and this time only the first column of my 3-second array of samples X, and doing the same for the second column. So I'm creating 2 separate arrays, left and right. And let me execute this. What do I do with them? Left and right are here. Right now, I take the mid channel as the average of left and right. Note that I only need to say plus and minus here for the side, and that operation, as well as this normalization, will apply to all the samples in left and right and their sum. Okay, same thing for the side. Instead of summing, doing the average, I do half of the difference. Okay, that's a conventional way to define psi. Okay, so let me do that. And mid and side are here, same dimensions. And now I do something which is slightly new. I take my side and I multiply by a gain greater than 1. By doing that, I create a new vector side that I use to invert this operation and go back to a left and right channel, summing the mid to the new side and taking away the new side from the mid. I have 2 new channels, left new and right new, that I then combine together or concatenate together using this also very popular MATLAB operator. It's based on the square brackets. It's called the concatenation operator. Okay, you put an array here and an array here, separating this case by a comma. The concatenation operator will form a new array by concatenating those 2 arrays horizontally. I can do that because both left new and right new have the same number of rows as here. So by executing here, I obtain a new array X new that's got the same dimension data types as my initial 3-second array X, but it will be different. And what I do here is that I use again the concatenation operator, this time though with a semicolon in the middle. What does this do? Instead of concatenating horizontally as with the comma, is concatenates them vertically, which is also possible here because X and X new have the same number of columns. So they can indeed be concatenated vertically. And by doing it, I have first the original stereo signal and then the expanded stereo signal. Why expanded? Well, because it had an amplified side as specified it out here. Okay. By doing that and by giving the result to the sound scale command, I will listen first to the first 3 seconds and then to the second 3 seconds. So let's do that. Right. So hopefully, really, I'm hopeful about that. The sound is getting to you in stereo mode. You're able to listen in stereo mode. You will have appreciated that the second version was expanded in a stereo, in a perceptual meaning. Okay. Right. So now we've got all these common. We've done something interesting. The interesting bits that we've done are from here around, from line 15, where we create the mid and side, and then possibly here to 20. And these things are fine. They are within this script, but it's useful sometimes to encapsulate all those commands together. And a useful way to do that is to create what we call a function, which is what I have here. Okay, let's put it here to the side. A function is a useful way, as I was saying, to encapsulate command and to make them callable more easily from another program. So what we have here is exactly what we had in our reference code to the left right down here. I'll let you appreciate that line by line, although here I have a more compact syntax because I don't create the intermediate variables left and right. I'm taking really left at the first column of X and right the second column, doing the average. Same thing for the side with a minus sign. I'm multiplying the side by this gain, okay? In this case, I had a hard-coded number. In this case, gain is a variable, and this variable is given to me through what we call the function interface. Okay, you can see that in this case, we started our code with this keyword function to say that this file for us encapsulates a function. And a function can be called with this name by passing in these two variables, our in this case, the array of audio stereo audio samples, a scalar gain, and it will return the results here, which is the recombined expanded stereo sample formed of mid plus side on the left channel and mid minus side on the right channel. Okay, so what makes this different from the code that we had here is that now we can call all these commands using just this syntax. So if you look at what I have here at the left hand side here, I've got a bit of code that calls my function by saying stereo width, passing it x, passing it a variable gain that I define here. In this case, I've got 1. And then in this case, I'm also plotting it. So by having one line of code, I'm calling all these different lines of code, and I can easily pass different values of these parameters and see what happens. In this case, for example, if I play this with a value of 1, I have the original signal and the original plot. Let's do it once. Okay, I'm sure most of you will be familiar with this plot down below here. This is the right channel against the left channel. So for mono signals, this will be a straight line, diagonal line, because the two are the same. So the various samples left and right will be distributed all over the diagonal. Let's try it. Okay, straight line. And if I give this a value greater than 1, you will see that those 2 points will be more spread out from away from the diagonal here. Okay, as well as sound, obviously more spatialized. The sound for us was down here. In this case, always part of the same cell. Okay, so I think I would say this is quite useful. This is a situation where we have our code encapsulated in some way, and then we have a way to change the parameters interacting. In this case, these sliders are made available by the live script, but you could think about simply changing this value by hand and experimenting what's going on. Okay. So now what makes this way of organizing code, which is already encapsulated, which gives us a way to change parameters, possibly also interactive, makes it different from what I would see if I had this algorithm, so the star expansion algorithm expressed as a plugin. Okay, in this case, executing in Reaper, as you've seen in the video. Let's try it. Original. Progressively taken to mono, and then expanded, right, up to a maximum value of 4. So the question is, what makes this different from this? I'll answer this question myself to make things quicker. So this gives us a way to change parameters as the audio flow through the algorithm, and we can interact with the algorithm as the audio flows, and the algorithm is processing the audio, the input audio, one block or frame at a time, okay? Which was not the case in our MATLAB function down here. What also makes this different is that the way we define the algorithm in this plugin is standard. It abides by some rules, so when we load it into a hosting environment, like in this case Reaper, it will understand what goes on. In this particular case, obviously this is a VST algorithm, so this is abiding by a very strict set of rules. But more in general, if you want to express an algorithm in a way which makes it easily usable and tunable by a user, we need to force us to write code in a more organized way. So let me go back to my code. One first thing that I feel like pointing out is that in this case, I have two inputs. And I need to understand what those are, in what order I need to pass them. If I pass the first the gain as a first input and the audio as a second, obviously the code in here would not understand. Also, any user would know at least how I'm called, and then I would have to structure my code to be able to process to accept one block of samples at a time. For this simple algorithm, the code that I have here that's able to process a whole vector of recording is no different from the code that would process one block of samples at a time. But things may be different with algorithms with state. It's worth pointing out. I won't have time today to give you an example. Okay, let me show you an alternative version of this that I have over here that I call stereo with expander. So I give it the name of a thing instead of an action. That's pretty common with these different ways of doing things. Let's start from here. In here, we've got exactly the same 4 key lines of code or commands that I had on the right-hand side. I said exactly, but it's not exactly to the point, and I'll show you why in a second. The other difference here, I mean, this is still a function, but it's called process. It's not called stereo with. Okay, it's got a name that's standard. And also this function is in a context that's wider than it. Okay, it's in a file that starts with a keyword that says class def, and indeed this is a class definition, or sometimes this may also be called an object, as is an instance of a class in MATLAB. Not all MATLAB users are familiar with classes and objects and with object-oriented programming, but the lucky side is that this is simpler to do in MATLAB than it is in other languages like C++ or Java, okay? So it's worth taking the leap and understanding the few things that are useful here, because classes can help us encapsulate and organize code in a way that makes things a lot more clear for users and hosting environments. So what's one other difference here? This, instead of having the gain here, the gain was not a hard-coded number. It was a variable passed in through the functional interface. In this case, width is something slightly more advanced. In this case, this, you can see that it's expressed as plugin.width. Plugin is the first input here, is a way to pass in our own object. It's the equivalent of the this in C++. And this gives us a way to access a value that's available in here as a class property. So a class is a way to group together code, routine, functions as the one in here with data as the one in here, for example. This data was a property, or was a parameter that I was changing. But properties or data could be something else in these types of classes. It could be, for example, values that I compute only once and I cache in a property value. It could be states that I cache in property values. In this case, this property is public because I don't say anything here. In other cases, you could have private properties. This is public because this needs to be seen by the user. So the user sees this, it sets a value, and when I execute the code, this is the way to access that value from the inside and use it. Also very important about this function is that it's got a standard signature. It always needs to be written this way. The first argument will be the object, the second will be the input audio, and the output needs to be the output audio. For me, programmer, I need to be aware of that and always write the signature in that way and use the variables in that way. For a user, somebody who takes this code from the outside, they will be able to know that if this is a MATLAB audio plugin as indicated here, it will always have a process method. So when they need to process input, they can call that. They can do that if there's a user or if it's an automated way to consume this code. Okay. So I was telling you about audio plugin. Audio plugin is a standard way to define audio plugins in MATLAB. All you need to do, and besides doing the right things over here, is that when you create a class definition that for you needs to be an audio plugin, you put the less than sign followed by this audio plugin with capital P. If you're familiar with object-oriented programming, well, this is saying that this concrete class is inheriting from the audio plugin abstract class. If you're not, just ignore what I've just said. Okay. So this way of writing plugins is already useful to use that in the way you're familiar within MATLAB. So if I put this quickly to one side here, and I show you another script that I've got here, this shows you a way to just call an algorithm on stream audio and tune it interactively from within MATLAB. Let me show you quickly. This is a simple MATLAB script, a more traditional way to organize code. It doesn't encapsulate the output. It doesn't give you the ability to format the text. You have comments here. And let me execute this cell of this script, this section. Okay, here I've got a spectrum analyzer. You've seen left and right channel overlapped because this is the first channel of the input and the first channel of the output. And when I have one there, this doesn't change. When I go to 0, these are separated. You're listening to all these audio drops just because the video capture is putting my old lap loop to strain. This has no reason to drop a priori. This is just a way to change this parameter interactively and see the results down here. Okay. So let's take a look at a bit more closely at this code. This is a simple while loop, and this encapsulates the idea of taking live input from possibly, in this case, a file visible up here. Okay, audio file reader, same file that we were using before, and doing it a few samples at a time. Samples per frame here, 512. It could be smaller, it could be larger. So this is a 512 by 2 array that I pass to the process method of my expander that I define out here earlier in the loop. Okay, and the input I write it to an audio device writer, which is a way to wrap a sound card as this is it, the outright, which is it was a way to wrap the sound card outputs. Okay, and so and while I pass the input audio to the audio expander object here, and I press to get the output, I also have an opportunity to pass the object to this function parameter tuner that takes the code in here, understands that there's one parameter to tune, and paints the parameter as I want it displayed to let me tune it. Because the object was created outside, I could pass it to this function before I enter the function, and while I execute, well, before I enter the loop, and while I execute this loop, this function has access to the object. So when I tune it through the interface, that value can be propagated to the object because this is the same as that is executed out here. And so when it enters here, it will execute. You can see that also if I execute this again and change value, I can go down here, put a breakpoint here, and stop. Verify that the input that I have here is 512 by 2, and then the value that I have here is exactly the one that I tuned and reached through the interface, which is 2.61. Okay. So why have I shown you this? To say that this is enough to express code in a way that is standardized and ready to be tuned from the outside. Actually, it's almost enough, because if you go back to, for example, Reaper or even the interface in MATLAB, there's something specific about the way this parameter was tuned. It had a minimum that was 0, it had a maximum that was 4, and it was going from 0 to 4 in a slightly specific way, because here in the middle, the value was 1. Okay, so this was not linear. This is not 0, 1, 2, 3, 4, as we'd expect. So there's a specific way to scale values from here to here. So there's some additional metadata that I need to specify, and was already specified here, although I hadn't shown it to you. This is a bit of ugly code. So this is the type of code that you copy paste, but this helps whoever consumes this code in an automated way know what you want to do with that parameter. And this says that you actually want to take that width parameter and you want to create a control for that, a control with a minimum of 4, minimum of 0, a maximum of 4, and with a mapping from min to max done as a power of 2 in this case, but that could be log, could be linear, etc. Okay, if you specify all of this, you're not only ready to automate painting user interfaces using MATLAB like this, and you're ready to process audio in a streamed fashion, you're also ready to generate plugins from this. And this is what I'm doing here. If I take the name of my class that I was also using here to create an instance of it, and I use it through this command, generate audio plugin, let me execute this section. You take this MATLAB code, you convert it to C++ under the hood, you join the algorithmic code right here with a right plugin interface. In this case, we're using Juice under the hood. Well, then the output of this will be a BSD plugin, because what we're doing here, again, is generating code, putting it together with plugin interface, generating a Juice project under the hood, and then compiling also that Juice project for you. Okay. So all of that things in this case will happen and will work. And what we've done, this generator plugin is made available with a toolbox called Audio Toolbox. What we've done is to package this whole thing together to make this transition as seamless as possible. And the idea here, again, is to enable people who write code to do signal processing to do this transition as quickly as possible. Always, there's always the few caveats, right? So we are taking this code and translating it to C++. In this case, this is possible, but it's reasonably easy to think about examples of writing MATLAB code that are not easily translatable to C or C++. So this is to keep in mind. Or the way to write MATLAB code so it's supported to generate C or C++ is documented. So when you write code that it's intended to generate a plugin, think about that. Go and read the documentation, see what's allowed and what is not. Okay. Other things. There's when you do this, you generate, I was saying, C++ under the hood, and you only need Audio Toolbox. The ability to convert MATLAB code to C and C++ has been around for a while, and it's best known to people as enabled through a product, an add-on product that's called MATLAB Coder. And that product is used to take MATLAB code and give you source C or C++, and then you can go away and do whatever you want. with. Okay, in this case, we're not doing that. We're giving you the binary. So all you need is really Audio Toolbox. Don't think that you need MATLAB Coder. Although if you go to the online documentation for a MATLAB Coder, which is accessible, that will tell you what's allowed and what is not. All right. If you have a license of MATLAB Coder, what you could do here is to add a flag in this command, a flag that has -juice project, and that will give you a zip file that you can open in Producer and give you the whole ready-to-build project that you could go in and modify. For example, to change the type of output plugin, to change the user interface yourself, and to take the project further. Okay, so that's another option that I don't have the time to discuss today. Another thing to keep in mind is that even if you write good MATLAB code that doesn't give you errors in MATLAB that translates to C++, you could always think about doing something stupid if you're clever that could possibly blue screen your plugin, and hence also your plugin host, your DAW, and your system. Okay, so we could have thought, okay, we should definitely push people to write the unit tests, do things properly. We know that a lot of MATLAB users are spoiled because doing something that, a mistake in MATLAB, throwing an error is not that bad. Okay, you get a red message and a chime, but so not many people like not many MATLAB users are used to regular software development, unit testing, and those rigorous approaches. So we created an additional command here that you can see here. I won't execute it for short. It's called validate audio plugin. Before executing generate audio plugin, we encourage people to run this. That would take your MATLAB code and test it in a few different situations with frame sizes of different length. And then it will generate code and do the same tests. And so it will ensure that your code is robust enough so that we're reasonably confident to tell you, okay, you're good to go and generate your plugin. Your code is very unlikely to crash. Okay. All right, while I was talking you through all these different aspects, this has finished executing because this line has been reached and I can see the output here in my command window. That means that I've produced here in my current folder a DLL because I'm running in Windows. On the Mac, you would have a dos.bst. Now, this is your BSD plugin, which is ready to go. In order to use it within a host environment, you need to go to your effects button here. In this case, we have it loaded, but we can remove it. And first of all, you need to go to your options and make sure that the plugin lives in a folder that is within, in this case, your VST path. Your VST path is available here in Reaper, for example, but any hosting environment's got its path. And here I have a number of folders included here in my path. One of my folders here is this C MATLAB VST plugins, where I can optionally directly generate my plugin if I provide an out directory flag here with the right folder. So instead of generating a plugin in this folder as I was doing, I can directly generate it into a target folder that is already within the VST path of my host. So then I can go to add, possibly refresh this list and find my my generated plugin here in this case. Okay, and here it is, and this is just what you saw before. Running natively, C++. Okay. Now, one of the things that I haven't told you about in this session includes customizing the plugin interface. So I just wanted to give you an idea of the kind of things that are possible these days. There are ways to, instead of having the default horizontal slider, you can position that slider vertically. You can lay out your different controls over the canvas. You can have different types of controls, such as knobs, switches, and other sort of things. Okay, this is probably not enough to, as I said at the beginning, to give you the ability to develop professionally and commercially valuable plugins. But it gives you the ability to structure your interface so that a user can interact with it in a meaningful way without too many assistants. All right, I think this is quite enough in terms of what I wanted to show you. So let me quickly go back to my slides and try to point you through a few other resources. So that's where I wanted to go. Right, so There are many things that I haven't told you about. I'd like to list them, at least the most important that came to mind, so you can know where to go to take a look at a few of these topics yourself. So first of all, I haven't go into details on how to create a plugin with states. The example that we've gone through was stateless, so it was because it was simple, but additional attention, additional care is necessary when you plug in and your algorithm has states. Now, there are a number of things that are built into MATLAB these days, specifically into Audio Toolbox. Fundamental audio processing algorithms like equalizers, parametric graphic, dynamic range processing algorithm, fast convolution, you name it. So I haven't gone through any of these. You're more than welcome to go and explore this before reinventing things from scratch, because they will also generate code. So if you use them in your plugin, you'll be able to generate also a VST plugin from them. I haven't tell you anything about how to profile code, although that's important. I won't hide behind a finger and say, MATLAB is efficient out of the box. MATLAB can be actually very efficient for audio processing and real-time prototyping, but it can also be slow. And that slowness, that bad practices in programming, can propagate to the generated C++. So it's useful to profile your code starting from MATLAB to understand where the bottlenecks are. And there's a few things to say which I haven't today. I haven't told you in detail how to code in MATLAB for generating C++. I've just told you that it's good to pay attention to it, because not any MATLAB code can generate C++. I haven't told you anything about how to configure MATLAB to access the compiler and use it. It's straightforward, but it's important that you remember that you need to do it. Check what other compilers supported to generate plugins, and install it and configure MATLAB to use it. I haven't told you anything about how to verify that the plugin that you generate is numerically equivalent to your MATLAB code. And a good way to do it is to use MATLAB as a plugin host when you host plugins in MATLAB. And that's not just limited to the plugins that you generate, but applies to any plugin available there that these days you can use in MATLAB. That plugin becomes an object in MATLAB. So you can tune it using a programmatic approach by saying plugin object dot property equals value, and that can help you also quite easily ensure and validate that the plugin that you generated is numerically equivalent to your reference MATLAB code. I showed you that you can customize your plugin UI using a few useful ways. You can also customize the appearance of your controls. So all of that is documented, but I haven't shown it to you. And I also haven't in detail show you how it works to export your project, to choose and to open it up. Okay, and there will be a lot more things that I haven't shown about. So, but you don't need to rely entirely on what you heard today. Associated with that competition that I talked about at the very beginning, there's also a resource pages on mathlix.com. The link is below. On this page, you'll find also a button to get a free license to use MATLAB to take part in this competition, which will have all the add-on products to enable you to get started quickly. It will also have a list of technical resources. Okay, it's a ton of things here. Specific links to documentation for really relevant things that are useful to authoring plugins. If I had to call out the first things that I suggest you to look at. One is this 4-page paper submitted at the AAS conventions a few years ago, when this workflow for generating audio VST plugins from MATLAB first became available. And then there's this 1 hour and a half online video that goes through the same things that we went through together today, along with a few more of the things that I haven't mentioned that are listed on the page before. And there's more here, okay, including a link to a gallery in the MATLAB documentation with pre-built examples of plugins that you can use and generate VST plugins from right away. They're ready to go, but you can also go inside, understand how they're made, slightly modify things to start writing your plugin, not from scratch, from existing example, okay? Another useful place to go is the submissions to the previous years. Here I'm listing just the ones from last year. You can see that the first place, you see the submission by Kristen Steinmetz, who I know came to this meetup probably a couple of sessions ago. All of these submissions have video code. Christian has, as well to go with it, a wonderful website. And if you use the tag here below to look in MATLAB Central, which is the code sharing website for MATLAB code, you will be able to go also to the submissions from previous competitions as well as the tutorial code. Okay, now this is the link that I made available. It's going to be available for about 4 weeks, where to download these slides as well as all the code that you've seen today. Okay, you can take a snapshot of this and then very patiently find it again. We'll try to put it in the chat window when I stop, so you'll have a way to get here and access the code in the slides. I also suggest that if you're a student and if you intend to take part on the competition, so you're most than welcome to email me about this session if you have questions, but especially send me an email so I can put your name down and your email address to a mailing list for announcements. We'll use that list to announce further tutorial, but also to give updates about the dates for this competition. In this COVID situation, we're trying to stick to plans. The deadlines for submission were supposed to be around mid-August, and to be able to organize the showcase and awards on time for the AES convention in New York in October. But things are getting very weird. Obviously, this year, we're not sure that we'll stick to plan exactly. And so please do subscribe to an announcement. That will be very useful, because we'll try to make things clear as soon as we know about them. Okay, and with that, I'll try to wrap things up and stop and open up for questions. Thank you.
Yeah, hi. Yeah, Gabriele, thank you so much for this talk. We have actually quite a few questions.
Hey, great.
So let's start with, so quite a few people are wondering about the code that is being generated under the hood. So Joseph asks whether we actually have access to the source code of the compiled plugins that's being generated. And then Jose asks how readable that code is, if we do have access to it.
Yeah, let's talk about that. So the process that takes MATLAB code and generates C++ has been existing for a while. And I guess the difference between seeing it or not is just a licensing thing. So we try to make this workflow available without asking people to pay the premium for having C source from code generating from MATLAB. So you just need to have MATLAB Toolbox, which is a normal toolbox, obviously not for free, but it's a relatively modest cost, especially if you're a student. So if you have that, you get the binary. If you want the source, then you need just to add a license for another product on the machine where you generate it. It's called MATLAB Coder, and that can give you either just the source code from the MATLAB code, so the source C++, or if you use that workflow generator plugin with the right flag, it will give you a ready-to-build juice project. You can open in Producer, and obviously everything will be open there. In terms of readability, so the code is designed to be readable. Anything that is generated by a machine will be sometimes less readable, well, often less readable than the one authored by an experienced and good programmer. Now, it was quite easy for us to make very readable the juice code, the code that's all around the plugin interface. That should be really the same as you used to write it if you are. And then there's the algorithmic code. So it will go in different places in different files. The algorithmic code, it's the code that you put together, and then there's the source code for all the algorithm that you use. There was a question about, for example, using LU factorization or many other things. Yeah, the vast majority of those things, unless there's a limitation in the doc, is supported. And so, but when you get the code for the LU factorization, that's not probably code that you want to go in and modify. First of all, it might not be all that readable. It's reading. You should definitely be able to make sense of it. It will not be pretty. And then you always discourage to go in and edit that code, because that really breaks that magic in between the MATLAB code that it's easy to interpret and then the C code that's supposed to be implementation.
Right. Thanks. Yeah, we have another question. Quite a few questions about performance. That seems to be the other kind of main concern. So Architect asks, how performant are the resulting plugins? And they also mentioned that Unity actually has some problems with generated code. And then Josep says that they have implemented quite complex stuff with MATLAB, including vocoders and denoising, spectral re-enveloping, stuff like that. And how efficient would be stuff like that in real time?
Right. So in general, so this workflow is thought to not to generate professional things, but it should be reasonably performing. So the first thing is that the code that gets generated really depends on how you write your MATLAB code, and writing it's people is often surprised when I say, I've been using MATLAB for 20 years and I've been with MATLAB for 12. So I know how to speed up MATLAB code. I used to be an application engineer, so supporting customers. I used to get code and a couple of tweaks speed it up by a factor of 300. That's not always possible in other languages, because in MATLAB, you can do stupid things. It does let you do it. You don't have to. There's a ton of documentation on writing MATLAB code in a way that's efficient. It depends on how you structure it, how you partition it. It depends on how you use indexing. It depends on how you vectorize. It depends on a ton of things. Using the right functionality, for example, to do FRR filtering, to do convolution. You can do convolution probably, in 100 different ways, and some of those can be very bad. So provided that you use the right bits and pieces, building blocks, and your programming practices are good, then your generated C++ is a good mirroring of that code. So that too should be very good. There's a caveat though. When you generate C++ in MATLAB for other workflows, it's quite easy to plug in optimized libraries. For example, you want to use FFTWs when you run an FFT. You want to use a specific library optimized for Intel multi-threading where you use a convolution. For when you generate plugin things, it's pretty simplified, so it doesn't allow you to optimize things to the bone, but it should be reasonable. And it's also keep in mind that you're encouraged to always profile things starting from MATLAB, and then as you generate the plugin, just bring it in, and you can use the plugin just as you can use kind of a VST plugin or an AU plugin in MATLAB just as an audio plugin. It will be an object once you import it, and so you can profile it and TikTok it just as you would do with a bit of a MATLAB code.
Okay, thanks. Actually, one more question on performance, whether we can expect like vectorization-based speed to translate to a C++ code. I assume that, this is a question from Max, I assume that they mean stuff like SIMD and kind of vectorization, which,
right. Yeah, good question. SIMD is a good example of sometimes it's not about vectorization itself. Vectorization itself will be translated, but vectorization itself is important specifically in MATLAB because it means calling a function interface only once and crunching number for the rest of the time. In C++, everything is flattened out. So the impact that vectorization has is not as important as it has in MATLAB. But it's best to use the code that you expect to be efficient in MATLAB. Now, you won't get SIMD indeed in the generated code. And that's where things don't allow you to, at present at least, to step in very easily in plugins and swap things that you expect to have optimized outcome. So expect that you would get a reasonably efficient serial C++ in the code, in the plugin that gets generated by MATLAB.
All right, thanks. There's also, because you talked about juice, there's a question whether juice is actually used by MATLAB directly when generating plugins. And what I understood is that you actually generate a producer project, right? So you get like a full kind of juice project, which you can either compile then, or maybe even copy paste parts of it somewhere else.
It's correct. I mean, you can get. I imagine that always as a more advanced workflow because it's for more people that know more. But let's start from that. You can generate a producer project that you can just drag and drop in producer and export, say, to Visual Studio, whatever that is, or as code and compile it. Okay, and that's open. It's all source code. But you can also avoid doing that and just use juice under the hood. So MATLAB ships with a core of juice. It's not a distribution of juice for you to use. It's you shouldn't go there and find it, but MATLAB can do the whole thing. So it can create the project and compile it, and that's the easiest thing to do. And you don't have to worry about it. It just happens, and yes, what it uses is a specific version of juice.
All right. So maybe a couple more questions. So we have some about latency, because that's the other, apart from performance, that's the other kind of concern. So Full Kick Productions is asking whether there's a latency cost associated with the matrix processing versus the per sample processing. And then Max is wondering whether the latency is even actually reported at all, like, for example, to your DAW.
Great. So there's three different aspects, I think, about this. The first is the latency associated with passing audio in and out of sound interfaces. And that really depends on, so if you are in MATLAB and you're doing real-time audio processing in MATLAB, as you've seen, that really depends on the number of samples per frame that you use. That is the variable that establishes your latency. There's no specific latency going through the plugin except from the latency that is associated to choosing a specific block audio length of block of audio. So that's really what makes your system have a latency. And so if you imagine passing a block of audio or using whatever plugin with 32, 64, 128, 256 samples per block, that's the latency you incur. You don't incur any extra latency cost by coding a plugin with MATLAB, except if you do something inside your plugin, for example, using a ping pong buffer or anything like that, or using a frequency domain convolution. That depends on what algorithm you choose. Yeah, in that case, you definitely incur some algorithmic latency. Then there's the last aspect, which is reporting the nominal latency. That thing that plugins can do has nothing to do with what they actually do. It's what they think they're doing. And you can hope that if that was developed by somebody that does the right thing, that's the same thing that's happening. So right now, plugins already from MATLAB have no way of reporting that value to the DAW. We're working on it. So just stay tuned. That may well come out. I don't have any clearance to talk about future release. That's just the way we work.
But I get it. Like, I had been developing plugins for a while, and like I've seen that if it gets sufficiently complex and you have like complicated stuff going on, then figuring out latency dynamically and reporting it correctly to the DAWs actually can become really, really non-trivial and quite complicated tasks. So
you're right. And when we heard about that, let me say that we come out with new stuff every 6 months. Our releases have the number of the year. Like this year, we had 2020A, which is the spring release, and then it will be a 2020B, the autumn release. So stay tuned. As soon as the pre-release comes out, you can try it out. You can download it and see what's new.
Last question maybe for you from Max, whether you can say anything about the use of deep learning models in the audio plugin toolbox.
Yes, so that's a very good question. So things are not completely straightforward. MATLAB's got a ton of stuff these days new that came out new for deep learning. And yet things are not yet straightforward in that you use a network as you would use it normally in MATLAB and generate code. However, there's some tools that we haven't been able to ship, but we can make available that take a deep learning network developed in MATLAB and generate the very MATLAB code that implements that network. And that is completely compatible with C code generation. That's the kind of things that Christian used in his project. Christy, he must have talked about that a couple of sessions ago. And so he did use a convolutional encoder. He coded it up in MATLAB. He coded it up by hand to start with. But what he could have done is import kind of a Keras or TensorFlow network into MATLAB, then run that function that I can possibly make available if you get in touch with me, generate the whole MATLAB code for the network, and then turn it into C++. Again, no optimized library, so be mindful of what you're doing. If you've got a very large CNN with tons of layer, right now, today, that won't be super efficient using this approach.
We actually have one more question from Spencer here in the group. Pardon me. Who asks, are there any resources for writing real-time safe code with MATLAB?
Well, real-time safe is a good concept. I think it's especially interesting when you have control as an author. You have an API that allows you to play with multi-threading. MATLAB uses a ton of multi-threading, but it's all encapsulated from the user. So there's a lot of data parallelism and optimized libraries, but you don't get to create threads in MATLAB. And so real-time safe, I wouldn't have called it that way. But yes, this documentation in terms of, for example, how to structure code for real-time and how to optimize. So in terms from a performance perspective, it does do the best that it can in real-time.
I just figured out that if we have like questions to each other on this Zoom call, then we can actually unmute the mic and just ask them, right?
That's right.
I just didn't occur to me before. That's funny. Anyway, so yeah, thanks a lot again, Gabriele. That was really, really interesting.